All right, everyone, we are finally here. It is time for the first actual machine learning lesson, not some random math that you need to know beforehand. I will make one comment here, which before I start the lesson. So this one, I'm going to leave the most complicated part out. The most complicated part I'm actually going to do in the next lesson. However, to be ready for that next lesson, please take a look at the extra Khan Academy video I linked in the last lesson. You'll find the recording has a description and a Khan Academy link. Watch that one video, it will help you enormously. But with that out of the way, let's get started on machine learning. I'm not going to focus too much on making you memorize terms. Instead, I'd rather focus on giving examples. So when it comes to machine learning, I think there are lots of articles you can find online about, what is AI versus what is machine learning. Let me not bother with that here. However, if you think about these kinds of algorithms, whether you call it AI or machine learning, they often are presented as either way too simplified, oh, this is Terminator, or way too complicated, hey, this is a research paper. I'm going to show you the middle ground, which is that machine learning can be thought of as a framework for solving problems. By framework, I mean a repeatable tool that will allow us to pick out different components of a problem, different parts of a problem, so we can always think about it and how do we solve it in the same way. Now, because it has these distinct components, these distinct parts, machine learning, it can be kind of defined with three key categories, three things that you need to look out for. So when it comes to machine learning, we're often focused on some specific task, T. This is the majority of the algorithms that most people will ever work with. They're going to be focused on some very specific task, which I call T. Now, T is a kind of vague definition of a task, so let's instead look at some examples of what these tasks might be. Well, here are some examples right here. So let's say you have some runners and you're trying to figure out how does a runner's height match up with their speed. Are there any groups that you can create, any groups that you can find in how the runner's height and their speed relates? Let's say you have some X-ray scans of your chest. Can you figure out, is there a tumor in this X-ray or is there not? So you might look at this as classifying whether this X-ray has a tumor or it doesn't. And finally, well, given the words already typed in a sentence, what will you type? ... And I don't know if you know the answer. It's next. Very creative, I know. That's another example of a task. A task in machine learning, a very specific problem. So you can see, we have words as data, we have images as data, we just have statistics as data. There are lots of different things that we can do in machine learning, lots of different specific tasks that we can solve. Another part of machine learning problems is that we need to track some performance, P. By performance, I mean how well is our machine learning algorithm performing at the task, T. And when we're tracking the performance, when we're tracking, how well we're doing, this isn't like, oh, the algorithm's doing good on day one and it's, maybe doing excellent on day two. We want very specific numbers that we can use to track the performance of a machine learning algorithm. Let's look at some examples of these numbers. So you could have a spam detector and you want to count the number of spam emails that are not blocked out of the total spam, because that's telling you, oh, that's how many the algorithm got wrong. Or let's say you have a LiDAR on top of a autonomous vehicle. What a LiDAR does is it sends out laser beams in every direction, and the laser beams bounce back, and it's able to create an image of the environment around the self-driving car. So it's going to have pixels in the image, and it's going to say, okay, this pixel, that's part of a road, this pixel is part of a car, and so on with pedestrians and road signs and whatnot. So another number, remember, number has to be a specific number to track the performance of a machine learning algorithm, is the percentage of pixels that it's accurately classified. That's the key word, classified. That it's actually that it's accurately grouped as, say, a road versus a sign. Finally, another number, this one's a little bit more abstract. Let's say you have a scatter plot like so. You have some dots, and you want to graph a line of best fits like this. Maybe I'll do it in a separate color, like so. What is the distance between the line of best fit and all of these scatter points? We can try and figure out how accurate is the line of best fits compared to the scatter points. So these are all different examples of specific numbers we can use to figure out how well is the algorithm doing at the task we gave it. And this is where I'd love to highlight just a very specific analogy. This isn't just something for machine learning. This is something we can do all the time. We don't need to use machine learning. We can always just think, oh, I have this problem in life. What specific metric can I use to track my performance? We can ask ourselves that as a question. Now, there's one last key part of machine learning, which is that in order to get better at our task with the performance metric that we're using, then we need some kind of data so that we can learn, this is how we're going to figure out what to do here. This is how we're going to get better. So for example, let's say I'm predicting the price of a house. Well, I can use the house's size, location, number of bedrooms, so many other factors about the house so that I can figure out, what is the house's price? And that would be the task, what is the price of the house? We can have, let's say, a user on Amazon. We can look at what is their checkout list, what are their previous purchases, what have they searched for in the past? And we can use that data to figure out, are they going to buy these products that I'm recommending to them right now? So that's an example of the data that they could use to get better at a specific task. Finally, let's say you have an application like, okay, I have my face here and I have a ID card with a photo of me in some database. I walk into a building, they want to know, do I belong there? So they can scan the camera photo they have right now and compare it to the ID photo in the database. So that data could be used to solve that task of figuring out whether I am, someone that they recognize. All of these are different applications, but you gotta just think about these three things because they're very important. We can use them for any problem we're solving. What is the specific task that I have? What is the way that I'm measuring how well I'm performing? And what data do I need to improve my performance? You can ask that for any problem in life, not just machine learning. So there you go, philosophical takeaway. Now, if that makes sense, I'm going to move on next to comparing two broad categories of machine learning. Now, there's one easy one. Let me start with the easy one. The easy one that's easy to understand, that is supervised learning. Supervised learning is almost like you have a teacher who's going to mark a worksheet, and you have the algorithm as a student. So the teacher is supervising the students. They're saying, okay, I'm going to check your performance. So I'm going to look at the answers you're getting right and wrong, and I will tell you how you're performing on this worksheet so you can go back, try again, and improve over time. That's basically what supervised learning does. You have the answer, you take the inputs, and then you're doing your best to predict the answer given, the input you have. So in the teacher analogy, it's like you have the worksheet that you get, and then you're trying to predict the answers for that worksheet. And then at the end, you're gonna go back to the teacher. They're gonna tell you, hey, these are the answers that you actually got correct, and these are the answers you didn't get correct. I'm gonna draw this out here. You go from the input to make a prediction. And after you've made a prediction, then you're going to compare the prediction to the answers. So let's say we have this magical versus arrow, which means you're comparing something. I think we should make a graphical symbol for a comparison arrow. Just saying. So that's what's happening. Take the inputs, make a prediction, and then compare the prediction to the actual answer. This answer can also be called a label. So answer slash label, because it's a little bit like, you're getting a label on what is this actually. So what is this supposed to be? What is supposed to be the correct blank in the worksheets? Hopefully that's making sense. And I'll give you some examples in case that seems a little bit too confusing, too abstract. So let's take the first example. Let's say we have this handsome young fellow right here, and his name is Bob. What we want is we want to go from this image, so that's the input, and we're going to predict some name which is going to be, blank. We don't know what the name is. It could be Bob, it could be Sally, it could be John. Our job is to take the name, it's blank right now, that the algorithm predicts, and then compare it to the answer. The answer is Bob. So that's an example. Input is image, output is some name, that's the prediction, and then the answer or the label is Bob. Let's do another example. So let's say my house has 2 bedrooms, 1 bathroom, and a fancy schmancy swimming pool. Swimming pool, swimming pool, swimming pool. That's the right one. So this is the input data. It has 2 bedrooms, 1 bathroom, and a fancy schmancy swimming pool. I want the algorithm to predict the price. So the price is going to be the prediction. And PS, the value of my house is $550,000. That's not accurate, by the way. I don't have a fancy schmancy swimming pool, just on a side note. But that is the label. That is the output. That is the answer or the label. So input was this data about the house. The prediction was the price. And then we're going to compare whatever prediction the algorithm generates to the actual labeled price that we have. This is, pretty straightforward, makes sense, and we're going to focus mainly on this, especially at the beginning. However, there's this entire other side of machine learning, which is called unsupervised learning. Now, unsupervised learning it's a lot more mystical. It's like this purple mystical cloud. That's artistic symbolism right there. Now, machine learning with unsupervised learning It's a little bit different from what we have with supervised learning because we don't have an answer or label. We still have the inputs. We still have like an end goal in mind, what we want the algorithm to predict. But the instruction is basically mess with the inputs until you reach the goal. We're not like, okay, go work on this worksheet, fill out the answers, and then I'll, look at the labels that I have, the answers that are correct, and I'll figure out, is your prediction actually correct? Instead, we just say, here's the input, here's the goal, figure it out. It's a very figure it out mindset algorithm. This is obviously complicated, and there are a number of very surprisingly different algorithms that we can use in unsupervised learning. Whereas over here, this idea basically stays the same. You need an input, you need a prediction, you need the labels. But I'll give you a few examples just so that this isn't so abstract. So here's the first example. I actually like this example pretty much. Let's say you have this image. It's of a wonderful cat. I'm going to call the cat Tiddles. And you have this amazing piece of artwork that I drew here with all my artistic talents. These are the inputs that we're going to give to an unsupervised learning algorithm. And the job of the unsupervised learning algorithm, the goal that it has, is make these images look as similar as possible. So I want the cat to have like some kind of swirly thingies so that the cat looks like the swirly image. So we give it the input, we give it the goal, and now the computer can change these images however it wants until we get out a new image with like a swirly cat. Meh, that's like a swirly cat in my eyes. So that's the head, and over here are the eyes, and there you go. That's a swirly cat. So that could be the output of the algorithm. Yeah, like this. Now, I'm not going to tell the algorithm how do you reach that goal. I will just say, here's the input. Your goal is make them look as similar as possible. And it's a little bit complicated. How do we tell the algorithm, what looks similar or not? But, you can see the visual understanding. Here's another example. Let's say as the input, you have a scatter plot of some customer data, the height versus the weight of customers. So this person, this person might have a height of 170 centimeters and they might weigh 50 kilograms. We want to take this data and we want to find three groups in it. Let's say, for example, we're selling clothing. We want to figure out what are some different sizes of clothing we want to offer, so small, medium, and large. And to do that, we might try and figure out, okay, where are most of our customers clustered? What's the specific word we use? Clustered. Clustered as in grouped. So the algorithm might say, okay, I'm going to find three groups or clusters. And it might choose, okay, here's a cluster, here's a cluster, and here's a cluster. Keep in mind, we're not telling the algorithm how to do this. We're just saying, here's the input. The goal is find three groups, mess around with the data until you can get some groups. So we're not going to worry about unsupervised learning for a bit because, it's weird. It's purple and it's swirly and it's got weird looking cats. We're not going to mess with that. Instead, we're going to start off with unsupervised learning. Take in some input, make a prediction, and compare the prediction to the answer. So let's actually look into an example of this in detail. We're going to look at how do we represent the input, like notationally in a complex way. How do we make that end prediction about what we think is the right answer? And then finally, how do we compare the answer to the prediction? So let's get started with the inputs. How are we going to represent the inputs? In machine learning, we often use the symbol X to represent input and Y to represent output. So X is going to represent the input data we have. Y is going to represent the labels, the correct answers that we have. Now, we have X here. It has a special name, and it's called the features of an algorithm. So input data, it's also known as features, as in, this album features Drake or BTS or Rihanna, music features. So that is what we call X. And again, Y is called the label. So what is the correct answer that the algorithm is trying to predict? The algorithm will try to go from the features to predicting a label. Now, since we just talked about features in BTS, well, let's talk about BTS as a problem. So let's say that our problem is that we're going to be given the features X that are a song, that are the songs that a user has listened to in the past week. So that's the input data, the features. Our job is to predict whether they'd buy a BTS ticket. So like, yes, they would buy a BTS ticket, or no, they won't. So we can predict this. And of course, we're going to need, this is a supervised algorithm. So we're going to need a label. We're going to need the correct answer. So Y will be, yeah, they will buy the ticket, or they will not. An example of where this algorithm might be used, you might have a platform like Spotify. They look at, what songs has a user listened to, and they decide, should we advertise this BTS ticket to them? Are they going to be likely to buy it? So hopefully that problem makes sense. Now, when we look at these input features, we're going to break down the features so that it's not just like, oh, this is X, all of that data that represents the songs that the user has listened to. We're going to break it down per song. So we're going to have like, okay, X subscript, Fake Love. That's like one BTS song, if you don't know, if you're not a BTS connoisseur. Then another feature might be Boy X subscript, Boy with Love, another BTS song. And on the other hand, we also might have some non-BTS songs. So X subscript Godzilla, that's a rap song. X subscript Drag Me Down, that's a One Direction song. And X subscript Teen Spirits, that's a rock song. So we have all of these inputs, features. What we want to do is know, hey, has the user listened to this song in the past? The way that we're going to represent that is with a 1 or a 0. A 0 means they haven't listened to the song in the past week. A 1 means they have listened to the song in the past week. And you see we have 3 lovely users here, Alice, Bob, and Kathy. Looks like Kathy doesn't like listening to BTS songs, so that already tells us something about Kathy. Now, once we have these input features, X is the input data, we also are going to treat Y the same way. So Y, remember, is the output. It's the label, whether they have bought a BTS ticket or not. And, lo and behold, Kathy has not listened to any BTS songs, and she has not bought a ticket. Who would have guessed? So again, we're using 1 saying, yes, they have bought it, 0 saying, no, they haven't bought it. And if you look over here, well, awfully convenient that I have just a column, just a column ready to add another variable. Hopefully the input features and output label make sense. Remember, we have to generate a prediction. So we're going to use a variable just to represent the predictions that our algorithm makes. the variable is going to be y with a hat. That's literally what it's called, y hat. Technically, this symbol is like a caret. It's like a upside down arrow. This is red y hat. And this is going to represent what our algorithm predicts, which may or may not be right. So let's say the algorithm predicts, yes, Alice is going to buy a ticket, but no, Bob and Kathy are not going to buy tickets. So our job now is, given this input data, given these input features, we want to predict y hat, which is what we think each user is going to buy or not. And then we want to make sure that y hat is equal to the actual output. So we're going to compare y hats with y, the predictions we have, with the actual output. And our job is make them the same. That's what we want the algorithm to do. Hopefully that makes sense. I'll pause here so you can take a look at the table. All right. So I'm going to introduce a few other variables that are important here. Just a few pieces of notation. So notice that we have 3 users, Alice, Bob, and Kat. Each example here is one user. So when it comes to like any training data in general, we call these examples of the different features and the labels and predictions. So each row of input features, output predictions, and output labels is called one example. And you see here we have 1, 2, 3 examples. So we represent the number of examples with the character m. M randomly means the number of examples. Yeah, I don't know why. Computer scientists are weird. Anyways, that's m. We have another variable here. It's called n. N means the number of input features we have. So here you can see we have 1, 2, 3, 4, 5 songs. Each of these is a row. So each of these is a different variable, and each of these represents one input feature. So we have 1, 2, 3, 4, 5 input features. We're going to represent that with the letter n. So the variable n means the number of input features, which is 5. Next, some notation. So let's say I wanted to refer to this specific value here. What is the output for this example? What is the output for this user, Kathy? The way that I do this is I'm gonna assign a number to each of these examples. The number is gonna be 0 for the first example. So Alice is gonna be 0. Bob is gonna be 1. And Kathy is gonna be 2. Yeah? So this is the 0th example. This is the first example. This is the second example. Computer science is weird in that we start counting at 0 instead of 1. So if I wanted to get the value of the output of this user, Kathy, the way that I would do that is actually, if you can see here, y superscript 2, and the value is 0, as you just saw here. This value of y is 0. How did I get the 2 in the superscript? Well, this is the 0th user, as I just said. This is the first user, and this is the second. So y of the second user, that's equal to 0. That's why we have 0 here. Similarly, with a feature, we can specify, okay, which feature do we want? We want The Boy with Love, that song. We want the variable that measures has the user listen to that song. And if we put a superscript 1 here. That means for the first example, which is Bob. So we go to the first example, Bob. We go to this feature, Boy with Love, and we have 1 as the value. So that's why X superscript 1 subscript Boy with Love is equal to 1. I hope that notation makes sense. And that covers the first part. Remember, we have 3 parts of supervised learning. How do we define the input? So now we just learned how do we define the input. Next, we got to go from the input to the prediction. So let's talk about that. How do we go from defining the input notationally to the prediction, which is y hat? Up here, I just did it randomly. I was just like, okay, put a 1 here, 0 here, 0 here. Ideally, we have algorithms that do a better job than me and don't just generate random predictions represented by y hats. Let's think about a few ways to generate these predictions. Here's the first way. So notice how whenever the user has listened to a song, I can put a 1, and then when they have not, I can put a 0. So let's say Kathy, she's only listened to 1 song in the past week. Alice, she's listened to a lot of songs. Well, if I add up all those 1s and 0s, Kathy is going to have a lower sum than Alice, because, Alice has 1 plus 1 plus 1 plus 1. Oh, no, 1 plus 1 plus 1, that's 3. These are the input features. And then Kathy is going to have 0 plus 0 plus 1 plus 0 plus 0. So that's just 1. So when we add up all of these input features, just the x's, not the y or the y hats, that's the label, that's the prediction. Well, it turns out Kathy has a lower sum. We can use that. It's just saying Kathy listens to less music in a week, so maybe she's less of a music fan. So maybe she'll listen to fewer songs. Maybe she won't buy a BTS ticket. We can write that mathematically. Maybe we say, okay, how do we get a prediction? We can say, okay, add up all of the input features. So whether this variable is a 0 or 1, whether this is a 0 or 1, and so on. Let's add them all up. And we'll say, okay, if the user is listening to more than 3 songs per week, 4 songs per week, we can choose like an adjustable number. We can decide some number of songs per week. If the user is listening to more than that many songs per week, then predict yes. Instead of writing one number here, I'm going to set it equal to this variable. That's a theta. Theta can be assigned a value like 3, If the number of songs they're listening to is greater than 3, then we can predict that they will buy a BTS ticket. That y hat will be equal to 1. Otherwise, y hat is equal to 0. This is called a parameter. It's adjustable. A parameter just means an adjustable variable. So all of this part is fixed, and then this is an adjustable parameter. We can change it, If it's greater than 2 songs per week, if it's greater than 10 songs per week, then predict y hat equals 1, otherwise y hat equals 0. Now, this is okay as a way to predict, but it's kind of naive because, we're predicting BTS tickets. It matters a lot more whether the user has listened to BTS songs, the first 2 songs are BTS songs, than whether they've listened to rap songs or, rock songs. But here, we don't have any of that distinction. We're just like, yeah, whatever, it's all fixed, just add it all up, and then if they've listened more than, some number of songs, then predict that they will. But what we'd like is, look here, like fake love, Alice and Bob listened to it. They bought a ticket. Kathy did not. She did not buy a ticket. It really looks like, fake love has 100% correlation. Maybe we wanna prioritize fake love so much more. Like if we see that some user has listened to fake love, then we're gonna be like, yeah, we're gonna be 100 times more confident that they are gonna buy the BTS ticket just because fake love is that great of a song. I mean, come on. Well, We can do that. We can do that mathematically. The way that we do that, remember, right now, all of these input features, they just have a value of 1 or 0. What we'd like is like, these values should be like 10. When we're summing them up, they should be like so much more valuable. They should count for so much more than, a rock song, for example. So the way that we're going to do that is, look right now, we have fixed sum over here. It's always going to be the same, ones and zeros. And then an adjustable parameter that we can set on the right. Let's reverse that. So we'll fix the adjustable parameter on the right. We'll say, okay, it's always equal to 0.5. But then on the left, we're going to make the sum adjustable. The way we're adjusting the sum is we're multiplying each input feature, which is, remember, either 0 or 1, with a parameter, theta 1, theta 2, theta 3, theta 4, and so on. So this could be like theta 1 equals 10, because, fake love is really important. If this is a 1, we want to multiply 10 times 1. So it's almost as if this value, whether they've listened to fake love, it counts 10 times as much as just, this sum up here. And in contrast, let's say this is a rap song. Again, it can be 0 or 1. Well, maybe we set theta 3 into like, 0.1. We don't really care if the user has listened to Godzilla before. So if we do that, then, let's say they have listened to Godzilla, it is a 1, not a 0. Then it will be like 0.1, that's the parameter, times 1 is equal to just 0.1. It's not going to be worth much. It's not going to have a large weight in the sum. I hope those words make sense to you intuitively. I know they're new words. And then why did I pick 0.5 here? Well, look what we're doing. We're saying, okay, round up to y hat is equal to 1, or round down to y hat is equal to 0. So if we have a value greater than 0.5, round up. If the sum of all this is greater than 0.5, round up. And then if the sum is less than 0.5, round down. Round up to 1, round down to 0. Now here's a really key idea that you have to keep in mind here, really key. What an artificial intelligence algorithm does, what a machine learning algorithm does, the artificial part is we just define these different parameters, theta 1, theta 2, theta 3, so on. And then we say, adjust the parameters however you want. And then, I'll let you figure out how do you get the right prediction. The right prediction meaning the one that corresponds with the output. So these parameters, they're kind of like the settings, the dials and knobs of the AI algorithm. And when the algorithm is trying to learn, that's what it's going to adjust. It's going to change, maybe theta 1. It's going to make it bigger. It's going to make it, 100 because fake love is that important. It's amazing. It is a hugely important song. But then maybe it's just like, okay, let me adjust these parameters down. 0.1. Yeah, who cares about Eminem? We'll just make it like 0.001. So the algorithm can adjust these parameters. That's how the algorithm learns. I hope that's making sense to you. That's a hugely important point. So that's the artificial part of machine learning. That's actually what's going on behind the scenes. So let's always remember that. And now what we want to do is we want to improve upon this a little bit more because there's this one issue here. The one issue is, let's say that the algorithm, it decides that, fake love is so important. I'm going to set theta 1 equal to 1,000,000. Then it really doesn't matter, what all of these other values are. It doesn't matter if, there's a boy with love, Godzilla, whatever. Well, you can have whatever you want. But if you have like 1,000,000 times, let's say this turns out to be 1, then automatically, it's always going to be greater than 0.5. And that's like not much of a distinction if we have this one parameter and this one input feature takes so much more precedence and dominance over all others. So that's why what we have to do is we want to scale the sum that we get so that it fits in between this range, 0 to 1. Because that way it's almost like we're always rounding up or rounding down. So it makes a lot more sense. This sum can't be a million and it's always greater than 0.5. It'll be like, okay, 0.9, or it'll be like 0.2. It'll range from 0 to 1. The way we do that in math is we use what's called a sigmoid function. This is the Greek letter sigma. It represents the sigmoid function. Remember, the sigmoid function, this is function notation. It's just taking in a number at the end of the day. So you have, this parameter times a number. This is another number times a number times a number. All of these return products that are still just numbers. And when you add together a bunch of numbers, lo and behold, you get numbers. Yay. So this is just, taking a number and it's going to return a number, which we can compare to 0.5. Then y is equal to 0, 1, y hat is equal to 0, or y hat equals 1. So we still just have numbers. And I'll show you the graphical representation of a sigmoid function first. So over here, you can see I take in some input x, I pass it into the sigmoid function, sigmoid of x, that's the output. It's going to range from 1 if, I have a larger input x, to -1 if I have a smaller, sorry, the output is going to range from 1 to 0 if I have a smaller negative number. So 1 is the output if you have a large x, 0 is the output if you have a small x, and like 0.5 in the middle. So that's what the sigmoid function does. It takes whatever large number you throw at it and it compresses it from 0 to 1. And we're going to write this as sigmoid of x. This is the formula. You don't need to worry about it. You don't need to know how it works, but you just take an x, you put in 1 over 1 plus e to the negative x. So x is a number, e to the negative x, if you don't know. E is like a constant in math, just like pi is a constant, so it has a fixed value, right? It's just like pi. E is about equal to 2.7. Just some trivia. But you don't need to understand this formula. If you do want to understand this formula, you can find videos. I'll link to it in the description. But the key idea is it just takes this sum, which could have been really big, and it makes sure it's between 0 and 1 so that we get an accurate rounded result. Make sense? I hope it does. Now, the only problem here is like we kind of have a bit of a mess. Like we have this huge expression here, and then, you have this formula here. So I'm going to try and clean this up a bit. The first thing that I'd love to simplify is all of this business right here, where we're multiplying these parameters with these input features and then summing them all up. If you recall, last time we learned about a neat trick that we could do with vectors in order to be able to do this. So let's take a look. Let's say we take all of our input features from Fake Love, Boy With Love, Godzilla, Drag Me Down, Teen Spirits, all of these different variables that represent whether a user has listened to the song in the past week. And we put them into this big vector that we're going to call capital X. And it's just all of those values. So it could be like 0, 1, 0, 0, 1, for example. And then we do the same thing with the theta parameters. So this could be like 10, this could be like 0.1, this could be 3, this could be 15, and so on. So we just took the parameters, put them all in one vector, put the input features, put them all in one vector. And we can just write theta transpose dot product x. And if you recall from the lesson on linear algebra, those matrix operations, this is quite by definition defined as this entire sum. Remember what's happening is we match up the first element here, multiply them, then add with the next element, multiply them, and add with the next element, multiply them, and add, and so on. So immediately we can simplify what we wrote about. We can just write this. Take the sigmoid of all of this business, which just means, all this stuff, this long thing. And if it's greater than 0.5, then, well, y hat is equal to 1. Or if not, then y hat is equal to 0. Remember, y hat is our prediction. So we've done that. I'm still going to simplify this a little bit, and I'm going to do it by breaking this all up into more equations so that it's not just, one giant clump. First equation is going to be just this part, just multiplying the parameters with the input features. I'm going to say z is equal to theta transpose dot product x. And z means, it's a variable that means the weighted input. I know, again, weird variable names, but that's what we call it. Z, weighted input. It's called the weighted input because we took the inputs and then weighted them by multiplying them with the different parameters. Hopefully that makes sense. Then we're gonna take z, which remember is the sum of all of these parameters times these input features. We're gonna put that through the sigmoid function, and then remember we get out a number between 0 and 1. So we put in a number as an x, we get out a number between 0 and 1. That we're gonna call A. A is for activation, and actually this sigmoid function, it's actually one of many functions that we could use here, that we could apply, that where we take in the weighted input and get out what is called an activation. So the sigmoid is one of many activation functions. The reason why we call it an activation is later on, when we get to neural networks, we'll be using that term a lot. And you can look forward to that in a few lessons. We'll actually describe, okay, this is what an activation is. Finally, the output y hat, remember the activation is going to be between 0 and 1, so we can just round all of those activation values, and that's what y hat is equal to. So let's say like you have an activation value of 0.99, then it's going to round up to 1, which means in our data we're saying if y hat is equal to 1, then yes, they will buy the BTS ticket. So there we go. These are our 3 equations, and they tell us how does the model, how does the AI algorithm, how does it generate predictions given the input data, which is represented with X. And the model can change the predictions by changing the parameters. The parameters are this vector theta. So next, what we want to do is we want to answer the last question that we had. Remember, we had 3 parts. 1 is getting the input, we talked about that. 2 is predicting, an answer given the input, we talked about that. The last part is comparing the prediction versus the answer. So let's talk about that and we can wrap up. Yay! I know, almost done. So the way that we compare the prediction and the labels, so that's the answer, that's something called the cost, also called the error, also called the loss. And you understand, the error is the most intuitive definition here, because it's like, okay, how wrong is our algorithm? Well, if the y hat, the predictions over here, those ones and zeros are different than the labels, these ones and zeros, then, the algorithm's more wrong. If not, well, the algorithm's less wrong. And to start off with, we can just take an intuitive version of the difference, which is literally, take the prediction y hat and subtract the label y. So it can be like, okay, the prediction, we predicted that they would buy the ticket, but no, they didn't buy the ticket. So then we have 1 minus 0. And that's going to say, okay, there is some error here. It's like there's an error of 1. That's the difference between the predictions and the labels. There is one issue here though, which is that we don't just have, one prediction and one label. We have a prediction for each user or each example. We have a prediction for Kathy up here. We're predicting, no, she's not going to buy the concert ticket. And then we have a prediction for the other examples too. So instead of just saying y hat minus y, what we're going to do is we're going to sum together the differences for all of the predictions for all of the examples. So y hat of the 0th example, so that's Alice. Y hat of the first example, that's Bob. Y hat of the second example, that's Kathy. You take the difference between the predictions that we generated for each example minus the label, the actual correct answer, whether they did or didn't buy a BTS ticket, and then we add them all together. So you can assume like maybe this difference is 1 because the algorithm was incorrect, this was 0, and this was 1. So then total difference, the total cost, the total error will be 1 plus 0 plus 1. That will be equal to 2. I hope that makes sense. We also have a simpler way of writing this in math. Instead of, writing out, okay, this term plus this term plus this term, because all these terms are the same, they just change the example each time from the 0th example to the first to the second. We have what is called sigma notation. This is the capital letter sigma, which is different from the lowercase letter sigma. This was used to define the sigmoid function, which is, that function that takes the input and returns a value between 0 and 1. The sigma function is used to define what is called a summation operation. Here's how it works. So you just take I is equal to 0, so that's the first value. You plug 0 here where you see I, so y hat 0 minus y 0, just like this first term over here. Then you go to I is equal to 1, then I is equal to 2, and you'd keep going until you reach m. Remember, m is the number of examples. And once you've done that for all these terms, all the examples, you add them together. So by definition, this is just a concise way of writing all of this for however many examples you have. I hope that makes sense. Now there's one issue with this way of taking the difference, which is that, let's say like, this over here. So we predict that y hat is 1 and it turns out to be 0. So over here, this value would be 1. And then after that, we add, over here, we predicted a 0, but it turned out that the correct answer was 1. So look what happens. 1 minus 0, that's 1. 0 minus 1, that's negative 1. So 1 plus negative 1, we just get a cost of 0. And that doesn't make sense. That doesn't mean like, oh, we're not being wrong. We don't have anything wrong. Instead, it means like, oh, we had this one wrong in a different way and this one wrong in a different way, and the two cancel each other out. So that's not very helpful. What we'd like to avoid is not like a negative or positive sign in these differences. We don't want any negatives or positives so that they cancel out. We just want to add up all the costs across all the examples without worrying, are they negative or positive? There's a few ways we can solve this. The easiest way is instead of just taking the difference, you just take the difference squared. I just added a squared here. What that does is, even if you had a negative 1 here, if you square that, then you're just going to be left with a positive 1. So the squared effectively gets rid of the negatives and the positives. So, well, it gets rid of the negatives and only has the positives, so that when you add together, none of the terms cancel out. Now, one issue with this is now it's like getting quite large. You know, you have all of these terms being summed together and you're squaring them all. The cost can get pretty large, which will create some issues that we'll talk about in the next lesson. So the last thing we do is we just divide by m. So multiply by 1 over m, divide by m. That just means the same thing. Why are we dividing by m? Because remember, we're summing over m examples. You know, m in this case. So here, m is equal to 3, right? Because we have 3 examples. So what we're going to do is we're just going to take this notation, you know, this sum of all these terms, and we're going to divide by 3. And it's almost like, you know, we're adding this bit, then this bit, then this bit, and, you know, we're squaring in the middle, of course. However, if we just divide by 3 at the end, it's like we're taking the average across all the examples. The average is also called the mean. So that's why this formula here, it's referred to as the mean squared error. Why mean? Because, you know, we're taking the average, we're dividing by the number of examples, which is m. M is the number of examples. Squared because it's squared, and error because, well, it's an error function. It's a function that lets us measure the difference between the predictions and the labels. And there we are. That's it. So we just call this C. C is equal to the cost function, or the, you know, error or loss function. And that's the formula. Now, this is just one of many ways that we can compare the difference between the predictions y hat and the labels y. So there are many other possible combinations, but the key idea is, you know, mean squared error. We're just trying to figure out how do we take the differences, and this is the way that we track the performance of the algorithm, this cost. So that's how we're measuring, are we getting better over time? So now remember, we are getting the inputs, x, then we multiply them by adjustable parameters, theta, and then through that, you know, we get the predictions, y hats, you know, through that process. So we have the inputs here, we have the predictions here, and over here with C now, that's the way we track our performance. So we have all the pieces needed to make a supervised learning algorithm. The only way that we're going to be able to change the performance of the algorithm, though, is by adjusting these parameters. So we can set different values for these parameters, because x is always going to be the same data, right? It's the input. And y over here, that's always going to be the same, because it's the labeled output, you know? It's not like the user can change whether they bought the ticket or not. So the only thing that can change is theta, all of these parameters. And when theta changes, it's almost like we have this graph. We have this graph where we can pick different values of theta. Now, I understand, you know, we don't just have one value of theta, but this is a simplified assumption. We can pick different values of theta, and we'll get out different values of C. You can almost think of C as a function of theta, because, you know, the x part, that can't change, and the y part can't change. So we can write this as C of theta is equal to all of this business. So when we're doing that, what we want to do is sometimes the cost, remember, that's the way we're measuring performance, that's going to be higher. You know, this might be like a cost of 2, whereas this might be a cost of like 0.5. And what we want to do is we want to go from the higher costs to the lower costs. But we can't change the output, we can't change the input. The only thing we can do is we can change our adjustable parameters. So that's what we want to do. We want to go from these high costs where, you know, you have this value of theta or this value of theta, and we want to change the value of theta until we get to a theta that gives us a low cost. And that is the subject of the next lesson. So how do we go and adjust the values of the data parameters automatically so that we can reduce the cost over time? So that's it for today. I'll see you in the next lesson.